For the more orthodox proponents of the modern-day ancient astronaut theory, the existence of Nibiru is one of the primary tenets. According to the theory, Nibiru is a planet in the Sol system that is or was once populated by a race of beings. These beings were depicted in Sumerian cuneiform and are known as the Anunnaki here on Earth. One of the favorite arguments of skeptics and debunkers alike is that even if a planet on a highly elliptical orbit did exist, there's no way life could be supported on such an icy cold planet. Ironically, you will not find too many folks in the scientific community making such an argument. Nibiru is not technically a rogue planet. A rogue planet, also known as an interstellar planet, nomad planet, free-floating planet, orphan planet, wandering planet, or starless planet, is a planetary mass object that orbits the galaxy directly. They have either been ejected from the planetary system in which they formed, or have never been gravitationally bound to any star or brown dwarf. Nevertheless, through examining the possibilities on a rogue planet, we can ascertain the probabilities for the highly elliptical Nibiru in our own solar system. The sun gets a lot of good press. Nearly everyone likes sunny days and rainbows. Solar panels are virtuous. Sunlight drives photosynthesis, which produces the oxygen we breathe. Our bodies make such mood-improving substances as vitamin D from sun exposure. Sun worship and solar deities appear throughout recorded history. We love our sun. But does the sun live up to the hype? Do we really need it? Yes, we do. If the sun were to suddenly turn off, Earth would freeze over into an ice ball. Our planet's geological thermostat, the carbonate-silicate cycle, is useless without the sun. Lakes and rivers and ponds would freeze first, and then it would take decades, but the ocean would eventually freeze solid. Some heat would continue to leak out of Earth's interior at volcanoes and mid-ocean ridges, but eventually Earth would look like Hoth, the ice-covered planet from the film The Empire Strikes Back. Most of Earth's life would vanish. Earth was born and grew up with the sun. It's not playing fair to just make the sun disappear. Let's consider a different type of planet, an Earth that never had a sun, a rogue or free-floating planet. These planets don't orbit stars. They wander the stars. They are free citizens of the galaxy. It might seem like the stuff of science fiction, but several free-floating gas giants have been found in recent years. Our own gas giants, Jupiter and Saturn, are leashed to the sun on well-behaved orbits, but this might not be the norm in our galaxy. One study published in Nature in 2011 suggests that the Milky Way contains 2 rogue gas giants for every star. That particular study remains controversial, but most astronomers agree that rogue planets are common in our galactic neighborhood. And for every rogue gas giant, there are likely to be several rogue Earth-sized rocky worlds. There are likely tens to hundreds of billions of these planets in our own galaxy. A free-floating Earth would miss out on many of the things we enjoy on our actual Earth. There would be no seasons or sunsets, and with no sun to revolve around, no birthdays. But could a rogue planet support life, let alone a vibrant biosphere like Earth's? To have any chance of life, at least life like our own, a free-floating Earth would need liquid water. And to have liquid water, a planet needs to keep warm. But space is ridiculously cold, just a few degrees above absolute zero. How could a rogue planet stay warm with no sun? All planets generate heat in their interiors. Most of Earth's internal heat was delivered by the giant collisions that built the planet, a large portion of which remains locked inside its crust. This heat slowly trickles to the surface, providing a source of internal energy that has endured since the Earth formed. This interior heat will last for billions of years to come, but it's a puny amount of energy, 3,000 times smaller than the sunlight that blasts the Earth daily. A free-floating planet with no sun cannot afford to lose any internal heat. Like a person suffering from hypothermia, a rogue planet needs a really warm blanket. A layer of ice on a planet's surface can act as a strong insulator, locking in a planet's heat. If the ice layer is thick enough, then a planet can maintain an ocean of liquid water beneath it. But to prevent the ocean from freezing for billions of years, the ice layer needs to be at least 10 kilometers or 6 miles thick. Two of Jupiter's large moons, Europa and Ganymede, have oceans lurking under miles-deep ice layers and might be analogs for these icy rogue planets. Could Earth, if frozen, transition into this type of planet and still maintain an abode for life in the deep ocean? Unfortunately, no. Earth is too dry. A global ice layer would only be a few kilometers thick, too thin to act as a strong insulator. At best, Earth could possibly maintain local liquid water, for example near a strong heat source such as a volcano, but not a global ocean. A thick atmosphere can also act to retain a planet's internal heat and allow an ice-free rogue planet to maintain liquid water at its surface. The best atmospheric gas for the job is hydrogen. Hydrogen is a very efficient thermal blanket, and as a bonus, it doesn't condense but rather remains gaseous even at the ridiculously low temperatures of space. A free-floating Earth with a thick hydrogen atmosphere could keep its surface temperature above the freezing point of water. The planet could have lakes and oceans and possibly life on its surface, but its atmosphere would need to be at least 10 to 100 times thicker than Earth's. On a side note, arguments are also put forth by the skeptics and debunkers that the Anunnaki need for gold on Earth makes no sense. Well, actually, it can make perfect sense if you consider the potential atmospheric thickness required on Nibiru and the use of massive amounts of gold that would be required to repair defects in such an atmosphere. In fact, recent scientific efforts on Earth have demonstrated that gold nanoparticles are extremely useful in atmospheric applications in interaction with hydrogen and carbon dioxide. At any rate, lit only by distant stars, a rogue blanketed planet would be invisible to the human eye. Like Uranus and Neptune, it would likely have many different cloud layers. No starlight would touch its surface. The atmosphere would be so smothering that if you stood on its surface and looked up at the sky, all you would see would be darkness. Free-floating planets probably formed in orbit around stars. Planets grow within disk of gas and dust orbiting young stars. Starting from dust grains, a series of collisions grow ever larger bodies. Some capture gas and become giants like Jupiter and Saturn. Others, like Earth, are smaller and rockier and take millions of years to reach their final sizes and settle into well-ordered planetary systems. But these systems are often unstable. Gas giants are so massive that their gravitational kicks can launch planets into interstellar space. Free-floating planets are the popcorn kernels that escape from the pot. Many of them will have thick layers of ice or hydrogen blankets, and some will have a buddy if they keep their moons. Tidal heating on Earth, like rogue planets, from interactions with either its moon or its gas giant companion, could provide an extra source of internal heat. Even if it has liquid water, could life exist on a planet without a sun? Organisms on Earth's surface don't all rely on the sun in the same way. Some forms of life, such as plants and simple microorganisms, are directly dependent on the sun's energy. These beings are primary producers. They transform sunlight into chemical energy directly. Higher orders of life, including animals, rely mostly indirectly on the sun by eating primary producers. But scientists have found some organisms on Earth that do not need the sun. They are called chemoautotrophs, and they live on the ocean floor. They make their own organic carbon using energy leaking out from inside the Earth. These organisms form the basis of the thriving ecosystem found around deep-sea hydrothermal vents. Photosynthetic organisms convert light energy into chemical energy. In contrast, chemoautotrophs rely on pre-existing conditions, such as the strong changes in temperature that exist at hydrothermal vents, to drive chemical reactions. Photosynthesis is much more efficient. Its conversion of solar energy into biomass is more than 1,000 times more efficient than the conversion of internal heat done by chemoautotrophs. But that's on Earth. On a rogue planet with no sun as an energy source, life would have a strong incentive to more efficiently harvest the planet's internal heat. A free-floating planet's biosphere must be built on chemoautotrophs. Only chemoautotrophs can provide the organic carbon required by other more complex organisms. But because of their low biological efficiency, a biosphere built on chemoautotrophs would need a large amount of biomass to be productive. Instead of having one photosynthetic tree growing 1,000 apples, it would need 1,000 chemoautotrophic trees growing 1 apple each. Could life arise on a free-floating planet, or would it need to be seeded from somewhere else? Well, we can't be sure, at least not yet. After all, we still don't know how life originated on Earth. But there are several theories for the origin of biological metabolism, including the deep-sea vent hypothesis, which proposed that hypothermal vents provided a cradle for Earth's earliest life, and rogue planets are likely to be littered with hydrothermal vents. So life on free-floating planets could well be homegrown rather than implanted. So the next time a skeptic or debunker presents their old and fallacy-laden argument that life could never exist on a planet such as Nibiru, remember the science presented here and educate them accordingly. Also, I would be remiss in not pointing out that the actual science presented here also explains why Nibiru does not need to be part of a binary star system whereby it relies on a brown dwarf for its existence.